Hello everyone, welcome back to our channel. In January 2025, the AI industry witnessed an unprecedented disruption that sent shockwaves through global financial markets. DeepSeek, a relatively unknown Chinese AI startup, triggered the largest single-day market capitalization loss in US history, erasing $2 trillion in value from US stocks. Among the casualties was NVIDIA, which saw its market value plummet by over $500 billion in a single trading session. The catalyst for this market upheaval was DeepSeek's groundbreaking achievement, developing a reasoning AI model that rivals OpenAI's best offerings at a fraction of the cost. This technological leap challenged the fundamental assumptions about the resources required for advanced AI development. The scale of this disruption becomes even more remarkable when considering the stark contrast in resources between DeepSeek and its competitors. In this video, we'll explain DeepSeek R1 and how the AI model is able to outperform expensive and proprietary AI software giants such as Google, OpenAI, NVIDIA, Tesla, and others. We'll focus on the key architectural differences and concepts, and we'll clarify what is true and what is hype. You see, DeepSeek operates with comparatively modest assets, backed by a Chinese hedge fund, managing approximately $7 billion. The company maintains a focused team of 200 AI specialists, including several Olympic medalists in mathematics, physics, and informatics, and operates with roughly 50,000 GPUs. DeepSeek did this with a team of less than 200 people. Meanwhile, Meta, Google, and others have teams where their compensation alone exceeds DeepSeek's entire training budget. The combined might of Google, OpenAI, Amazon, NVIDIA, and Meta represents over $4 trillion in assets, thousands of AI scientists, and access to more than 1 million GPUs and TPUs. And yet their AI models were left in the dust by DeepSeek R1. The economics of DeepSeek's achievement are particularly striking. Their R1 model's base training, excluding ablations, smaller runs, and data generation, required GPU hours worth just $5.5 million. Even with reinforcement learning included, the total cost remained approximately $6 million. This stands in stark contrast to OpenAI's GPT-4, which reportedly cost $600 million to train, making DeepSeek's approach 27 times more cost-effective. The cost efficiency extends beyond development to operational expenses. OpenAI's models cost over $100 per million tokens, while DeepSeek R1 is less than $4 per million tokens. Furthermore, what makes this development even more significant is DeepSeek's commitment to transparency and accessibility. The R1 model is open source with a permissive license, and notably, it fully discloses its reasoning steps. Anyone can check their work. The code is public. The technical papers explain everything. The point is to highlight the importance of transparency and ethics in the global race for AI innovation. This approach not only challenges the traditional closed-source model of AI development, but also demonstrates that sophisticated AI capabilities can be achieved without massive infrastructure investments. This disruption has forced a fundamental re-evaluation of AI development assumptions. The notion that superior AI requires vast GPU resources and enormous electricity consumption is being questioned. As global attention shifts to China's emerging AI dominance, Silicon Valley's traditional technological advantage appears to be eroding. The DeepSeek breakthrough suggests that the future of AI innovation may lie not in overwhelming resources, but in clever, efficient approaches to model development and training. The Wall Street NVIDIA stock crash incident has particularly heightened awareness of China's AI capabilities, prompting many to take Chinese AI development more seriously. It demonstrates how a relatively small focused team with the right approach can revolutionize an industry overnight, amplifying the tremendous uncertainty and potential that exists in the AI space. DeepSeek R1's benchmark demonstrates that it performs at a similar level to OpenAI's O1 model on reasoning problems like mathematics, coding, and scientific reasoning. This performance is because of significant architectural changes. The model includes multiple innovations compared to traditional LLM architecture we know from Meta's Llama and other open-source models. There are 8 fundamental innovations and improvements that form the core of how DeepSeek R1 works. We'll go over these main architectural improvements one by one and explain what they are and how they will impact the future of investments in AI, model development, and to some extent the importance of ethics and transparency in the AI space. So here is a list of these 8 clever architectural improvements. 1. Mixture of experts. 2. Advanced load balancing for expert specialization. 3. Multi-head latent attention. 4. Multi-token prediction. 5. FP8 quantization. 6. Group relative policy optimization. 7. Integration of chain of thought reasoning with reinforcement learning. And 8. Model distillation. Together, these 8 concepts have opened up a new chapter in AI model development. The full impact of this disruptive development has yet to be felt beyond the recent stock crash of NVIDIA. But rest be assured, the race for artificial intelligence dominance is now going to include many new smaller labs and even several more countries. So let's begin with the first innovation, Mixture of Experts, or MOE. Mixture of Experts represents a groundbreaking architectural approach in artificial intelligence that fundamentally transforms how large language models process information. Rather than using a single monolithic network, Mixture of Experts architectures employ multiple specialized neural networks, or experts, working in concert to tackle complex tasks with unprecedented efficiency. Think of Mixture of Experts as a highly efficient organization structure for artificial intelligence. Instead of maintaining one massive neural network that must be fully activated for every task, Mixture of Experts creates a distributed system of specialized expert networks. Each expert develops deep knowledge in specific domains or types of reasoning, and a sophisticated routing system determines which experts should be consulted for any given input. In layman's terms, DeepSeek has built an expert system. Instead of one massive AI trying to know and do everything, they have specialized expert AIs that come to help only when needed. The efficiency gains from this approach are staggering. Traditional models must activate all their parameters for every computation. Imagine running an entire company's worth of employees for every single task. In contrast, DeepSeek's implementation of MOE achieves remarkable results with selective activation. For example, with a traditional models that has 1.8 trillion parameters, all parameters are active continuously, whereas with DeepSeek's Mixture of Experts, which has 671 billion total parameters, only 37 billion are active at any given time. This is a more than 95% reduction in active parameters while maintaining or improving performance. It's like having a huge team but only calling in the experts you actually need for each task, using an example of a large hospital system. Rather than consulting every doctor for each patient, the hospital routes patients to relevant specialists. You wouldn't need a cardiologist's input for a simple sprained ankle, just as a Mixture of Experts model doesn't need to activate its code-specialized experts when analyzing poetry. Number 2 on the list of innovations is Advanced Load Balancing for Expert Specialization. This is actually a further enhancement to Mixture of Experts concept. DeepSeek has implemented sophisticated load balancing mechanisms to ensure optimal utilization of their distributed hardware resources. This innovation prevents the common problem of expert specialization becoming too narrow or certain experts being overworked while others remain idle. The load balancing system ensures that an even distribution of computational load across available hardware occurs, a balanced development of expert specializations is realized, optimal resource utilization during both training and inference happens, and it prevents expert collapse from happening, where the system might over-rely on a few experts. There are many practical benefits of Mixture of Experts architecture that deliver numerous transformative advantages. For example, there is a dramatic reduction in computing resources needed for both training and inference due to the computational efficiency. The model is easier to scale by adding new experts without retraining the entire system. The specialization enables better handling of domain-specific tasks through dedicated expert networks, and there is more efficient and optimized use of hardware through dynamic resource allocation. The future implications of this architectural breakthrough suggests a new direction for AI development labs, where bigger isn't necessarily better, but a smarter organization of resources might be the key to future advances. The success of mixture of experts architectures challenges the assumption that we need ever larger models with more parameters to achieve better performance. Instead, it points toward a future where AI systems become more like efficient organizations, with specialized components working together under intelligent coordination. Many people might confuse this concept with AI agents, a hot topic in 2025, but the mixture of experts concept is slightly different. In the AI agents paradigm, different LLMs from different companies can be deployed, but in the case of mixture of experts, only experts within the DeepSeek R1 neural network are invoked as needed. The true potential of mixture of experts extends beyond current implementations. As we develop better routing mechanisms and more efficient ways to train specialized experts, we might see AI systems that can dynamically evolve their expertise and become even smarter based on usage patterns, while maintaining remarkable efficiency in computation and resource utilization. Number 3 on the DeepSeek innovations list is multi-head latent attention, or MLA. Multi-head latent attention represents a major advancement in transformer architecture, addressing the critical bottleneck of memory and computational demands inherent in the attention mechanism of large language models. In traditional transformers, each token must store its full key value, KV pair, in memory, and attention computations operate across the full dimensional space, leading to memory usage that scales linearly with sequence length and computational complexity that grows quadratically. Multi-head latent attention transforms this process by compressing KV pairs into a lower dimensional latent space, significantly reducing the memory footprint while maintaining attention quality. This innovation enables more efficient processing of longer sequences and decreases both memory consumption and computational load. The implementation of MLA involves 3 key stages. First, dimension reduction projects the original high-dimensional query, Q, key, K, and value, V, matrices into a more compact latent space using learned projection matrices that preserve essential relationships while reducing dimensionality by factors of 2 to 8. Next, latent space operations conduct attention computations within this compressed space, leveraging multiple attention heads for parallel processing and optimized matrix operations. Finally, information preservation techniques ensure that key relationships remain intact through carefully designed projections, skip connections to support gradient flow, and normalization strategies to stabilize the compressed representations. MLA delivers several critical benefits. It enhances memory efficiency by storing KV pairs in a compressed form, allowing for the processing of longer sequences within the same memory constraints, and achieving 2 to 4 times memory reduction with minimal impact on quality. Computational speed also improves due to the reduced dimensionality, lowering the number of floating point operations required and accelerating inference, especially for lengthy sequences. Moreover, MLA improves scalability, facilitating better GPU memory utilization, supporting larger batch sizes during training, and enhancing performance as sequence lengths grow. The efficiency gains from MLA result in the ability to handle sequences up to 2 to 4 times longer, reduced memory bandwidth demands, lower inference costs, faster training and fine-tuning, and more effective resource usage in production environments. MLA's development opens new avenues for processing even longer sequences, creating more efficient model architectures, and scaling attention mechanisms effectively. It supports novel applications requiring efficient attention computations and integrates well with other optimization techniques. Ultimately, MLA demonstrates that significant improvements in transformer efficiency can be achieved through architectural innovation rather than merely increasing computational resources. This advancement aligns with the broader movement toward making large language models more practical and cost-effective to deploy. Next up is number 4, multi-token prediction, or MTP. Multi-token prediction marks a transformative advancement in text generation by enabling the parallel prediction of multiple tokens, contrasting with traditional models that predict tokens sequentially. This shift significantly enhances both the efficiency and quality of language model outputs. Traditional approaches process one token at a time, resulting in higher latency and lower throughput, as each token must be generated before moving to the next. In contrast, MTP predicts multiple tokens simultaneously, allowing for natural phrase generation, improving throughput by 2 to 3 times and maintaining a 90% accuracy rate. The advantages of MTP are multifaceted. Its parallel token generation reduces computational bottlenecks, leading to faster response times, more efficient resource utilization, and lower inference costs. Additionally, by processing natural language in chunks, MTP maintains better contextual relationships between words, producing more coherent and fluent text with a reduced likelihood of losing context mid-sentence. Its advanced contextual understanding enables more accurate handling of idiomatic expressions and semantic relationships, thanks to its broader contextual consideration during predictions. Architecturally, MTP reduces attention computation overhead, optimizes GPU utilization, and scales efficiently with sequence length. Its technical implementation involves sophisticated context management through sliding windows of previously generated tokens and dynamic quality control mechanisms, including confidence scoring and fallback strategies for low-confidence predictions. Performance metrics highlight MTP's ability to generate tokens 2 to 3 times faster, reduce response latency, and improve batch processing throughput, while maintaining comparable accuracy to traditional single-token models. Its real-world applications span real-time interfaces like chatbots and live translation, as well as batch processing tasks such as document summarization and content creation. Looking ahead, MTP's success suggests future developments in architectural evolution and application expansion, including integration with streaming applications, real-time multilingual processing, and enhanced multimodal capabilities. This innovation by DeepSeek not only challenges the traditional token-by-token generation paradigm, but also underscores the potential for further advancements in speed and efficiency, demonstrating the profound impact of architectural innovation on AI development. FP8 quantization is the fifth innovation on the list of DeepSeek's masterstroke. FP8 quantization represents a transformative approach to model optimization, significantly reducing computational demands while preserving model performance. This innovation is especially impactful when combined with DeepSeek's other advancements, that is, mixture of experts, multi-head latent attention, and multi-token prediction. Unlike traditional neural networks that rely on 32-bit floating point numbers, or FP32, for high precision but at a considerable memory and computational cost, FP8 utilizes 8-bit floating point numbers. This reduces memory requirements by 75%, while maintaining sufficient accuracy for AI tasks. The technical implementation of FP8 quantization involves precision reduction, where 32-bit floats are converted to 8-bit representations with strategies to preserve essential numerical properties and maintain model behavior. Adaptive bit-width scaling dynamically adjusts precision based on the value range, optimizing bit allocation to prevent information loss and ensure numerical stability. Additionally, loss-aware quantization takes model performance into account during the quantization process, adjusting precision based on layer sensitivity to minimize accuracy degradation. FP8 quantization is applied across activations, weights, and key-value caches within attention mechanisms, improving memory efficiency by significantly reducing storage needs and enabling faster data transfer. Computational speed is enhanced through quicker arithmetic operations, better cache utilization, and reduced memory bandwidth requirements, which contribute to improved hardware efficiency. This optimization also lowers deployment costs, reduces energy consumption, facilitates easier model distribution, and improves compatibility with mobile devices. When integrated with DeepSeek's other innovations, FP8 quantization works synergistically to enhance efficiency. In mixture of experts, it reduces memory demands, allowing more experts to be included within the same budget and improving routing efficiency. For multi-head latent attention, it decreases the memory footprint of attention mechanisms, enabling longer sequence processing and greater computational efficiency. With MTP, it accelerates parallel processing, reduces memory usage during predictions, and boosts overall system throughput. DeepSeek's implementation of FP8 quantization reflects not only technical innovation, but also a breakthrough in training methodology. The team independently developed core concepts similar to those of OpenAI's O1, as validated by OpenAI's Chief Research Officer, Mark Chen. This convergence highlights a broader trend in AI research, where multiple teams arrive at similar solutions, reinforcing the robustness of these advancements. The practical application of FP8 has resulted in state-of-the-art performance, while maintaining model quality with fewer resources, streamlining the training pipeline. Looking to the future, FP8 quantization points to potential developments in both hardware and model architecture. This includes the creation of processors optimized for FP8, specialized AI accelerators, and more efficient memory systems. In terms of model development, new training techniques for quantized models, further precision optimizations, and novel quantization strategies are expected to emerge, along with integration into next-generation AI architectures. The success of FP8 quantization, particularly in combination with DeepSeek's other innovations, underscores that significant efficiency gains can be achieved without compromising performance. This challenges the prevailing belief that greater computational power is the sole path to improvement, paving the way for more accessible, cost-effective AI solutions. The sixth innovation by DeepSeek is Group Relative Policy Optimization, or GRPO. Group Relative Policy Optimization represents a significant advancement in reinforcement learning for large language models, offering a more efficient alternative to traditional methods like proximal policy optimization, abbreviated as PPO, and direct preference optimization, that is DPO. Unlike PPO, which requires a value function model and is computationally intensive, or DPO, which simplifies preference learning but is limited by the scope of preference data, GRPO eliminates the need for a value function altogether. It introduces group-based baseline estimation, reducing both memory and computational demands while maintaining or even improving model performance. GRPO operates through key mechanisms such as group-based baseline estimation, which computes baselines from group scores without the need for a separate value network. This approach reduces the number of parameters and enhances training stability. Its policy optimization process relies on a probability ratio and a group relative advantage, using a clipping parameter to maintain stable learning dynamics. GRPO integrates seamlessly with multi-stage training, combining supervised fine-tuning with reinforcement learning to progressively develop model capabilities while ensuring stability. The reward systems supported by GRPO are versatile, including rule-based rewards with explicit performance criteria, binary rewards that simplify optimization with clear success-failure signals, and general reward models that allow for nuanced, holistic performance assessments. Compared to traditional methods, GRPO offers notable advantages in computational efficiency, with reduced memory usage, lower computational overhead, and faster training cycles. It also enhances training stability through more consistent optimization, reduced variance, and improved convergence properties, leading to better reliability. In terms of performance, GRPO strengthens reasoning capabilities, generalization, task adaptation, and output consistency. DeepSeek's multi-stage training approach with GRPO starts with supervised fine-tuning to establish foundational knowledge, followed by GRPO-driven policy refinement and behavior optimization. The final stage focuses on developing complex reasoning, optimizing task-specific performance, and integrating advanced capabilities. This structured progression enables models to develop sophisticated reasoning skills more efficiently than previously possible. GRPO's practical applications are evident in its ability to foster advanced reasoning, such as logical deduction, problem-solving, complex analysis, and strategic thinking. It also improves model behaviors, enhancing helpfulness, alignment with user preferences, response consistency, and overall reliability. The success of GRPO has influenced the AI industry, with other labs and teams, such as Quen, adopting similar approaches, leading to new research directions and improved training methodologies that enhance model development efficiency. Looking ahead, GRPO's impact suggests significant potential for future technical advancements, including novel optimization techniques, new training strategies, and methods for better efficiency and scalability. It also points to an evolution within the AI industry, with more accessible development processes, improved training efficiency, and expanded application possibilities. By demonstrating that complex reasoning capabilities can be developed with fewer resources, GRPO challenges traditional assumptions in AI development and paves the way for innovative research and practical deployment. Number 7 is integration of chain of thought, reasoning with reinforcement learning. This is one of the most remarkable machine learning innovations by DeepSeek because it integrates chain of thought reasoning with reinforcement learning to create a dynamic, self-improving AI system. This combination marks a significant advancement in how AI models learn and enhance their performance over time. The chain of thought mechanism allows models to explicitly display their reasoning process by breaking down complex problems into clear, visible steps, making internal logic externally observable. This transparency enables real-time self-correction as models verbalize each logical step, engage in self-questioning, and demonstrate metacognitive awareness through reflective moments of realization and re-evaluation. Reinforcement learning complements this by mirroring natural human learning processes, emphasizing exploration and discovery. Unlike traditional methods that rely on predetermined correct answers, reinforcement learning fosters learning through interaction with the environment, refining policies based on outcomes, and continuously improving performance. The reward structure incentivizes efficient solutions, encourages exploration of multiple problem-solving paths, and reinforces optimal strategies guided by performance metrics. The synergy between chain of thought and reinforcement learning results in a powerful self-evaluation mechanism where chain of thought outlines the reasoning steps and reinforcement learning assesses their effectiveness. This integration helps identify areas for improvement, making learning more targeted and efficient. The process of error detection and correction becomes systematic, with each iteration building on previous experiences. Mistakes are transformed into learning opportunities, while success patterns are reinforced, leading to progressive enhancement in model performance. Performance metrics show that this approach yields notable improvements in accuracy and learning efficiency. DeepSeek R1 outperforms static systems like OpenAI's O1, Claude 3, Gemini 2.0, and Meta's Llama and others by exhibiting continuous growth and approaching near-perfect accuracy levels. The learning process becomes faster and more robust, with better generalization to new problems and a reduction in error rates over time. Imagine DeepSeek a year from now, when it has learned and improved itself by several folds. In real-world applications, DeepSeek's method excels in tasks such as mathematical problem-solving, where the model solves equations step by step, verifies its work, and corrects errors as needed. It also thrives in complex reasoning scenarios, including multi-step logical deductions, scientific problem-solving, strategic planning, and decision-making. Compared to traditional approaches, this method enhances learning quality through thorough understanding, superior error detection, and more effective problem-solving strategies. System efficiency improves with reduced data requirements, more effective learning processes, better resource utilization, and quicker improvement cycles. Looking to the future, this approach paves the way for technical developments such as more advanced self-improvement mechanisms, sophisticated reasoning patterns, and novel training methodologies, potentially making long strides towards artificial general intelligence, or AGI, the holy grail for AI labs. Practical applications will benefit from more robust AI systems with enhanced problem-solving abilities, improved human-AI interactions, and greater transparency in AI decision-making. To summarize this marvel, at the core of DeepSeek's innovation is the AI's capability for self-reflection, allowing models to analyze their own reasoning, identify areas for growth, and dynamically adjust strategies based on experience. This continuous improvement model eliminates static performance ceilings, enabling ongoing optimization and adaptive learning strategies. The integration of chain of thought with reinforcement learning demonstrates that AI systems can evolve to become more intelligent, adaptable, and efficient, capable of learning and improving autonomously without constant human intervention. And finally, the eighth DeepSeek innovation on our list is model distillation. Model distillation is a transformative approach that makes open-source advanced AI technology more accessible to all by enabling large, resource-intensive models to transfer their capabilities to smaller, more practical models without sacrificing performance. DeepSeek's implementation of this technique highlights how models with 671 billion parameters, which require thousands of GPUs and significant computational resources, can be distilled into models with just 7 billion parameters. These smaller models can run on consumer-grade hardware with reduced resource demands, lower operational costs, and manageable memory requirements. The distillation process follows a teacher-student framework, where the large model acts as the teacher, transferring knowledge to the smaller student model through examples, detailed reasoning processes, and step-by-step explanations. This comprehensive teaching methodology allows the student model to observe, internalize reasoning patterns, and develop similar problem-solving strategies optimized for efficiency. Chain-of-thought reasoning plays a critical role in this process, as the teacher generates exemplar solutions that break down complex problems, guiding the student to adopt explicit thought processes, problem-solving strategies, and decision-making frameworks. Reinforcement learning further enhances the distillation process, allowing the student model to refine its capabilities through iterative practice and performance optimization. Interestingly, distilled models often exceed their teacher's performance by achieving more efficient processing, better generalization, and improved outcomes on specific tasks. DeepSeek has successfully integrated these distilled models into open-source frameworks like Llama 3 and Qwen, demonstrating their ability to match or surpass many folds more larger models in areas such as mathematics, coding, and scientific reasoning, making them competitive with models like GPT 4.0, Gemini 2, and Claude 3.5, among others. The resource efficiency of distilled models is striking, with computing power requirements reduced by 99%, enabling single GPU operation and making advanced AI accessible to smaller organizations. Memory usage is also optimized, allowing standard hardware compatibility and efficient storage and bandwidth utilization. This breakthrough has significant implications, democratizing AI in a truly meaningful way by lowering barriers to entry, reducing operational costs, and promoting broader adoption across diverse applications. Looking ahead, model distillation opens the door to further size reductions, enhanced efficiency, new distillation techniques, and novel applications. Its impact on the industry is profound, fostering a more competitive market, encouraging innovation, and expanding AI adoption into new use cases. The revolutionary aspect of model distillation lies in the performance paradox, where smaller models outperform larger ones in efficiency and specific task handling, challenging the traditional belief that bigger models are inherently better. Ultimately, model distillation represents a fundamental shift in AI development and deployment. By proving that smaller models can match or even exceed the performance of their larger counterparts, DeepSeek has paved the way for a future where advanced AI capabilities are not only more widely accessible, but also more efficiently implemented, driving greater innovation and broader societal impact. Now let's look at how DeepSeek R1 model was trained. DeepSeek R1 model training consisted of a multi-stage training process comprising 4 stages. To prevent the early unstable cold start phase of reinforcement learning and training from the base model, the team started with supervised fine-tuning. This is because fine-tuning before applying group relative policy optimization can actually make the training process faster and more stable. Stage 1 is base to supervised fine-tuning. In this stage, up to 10,000 token-long chain-of-thought tokens are collected using the fine-tuned models R10 and human annotator. The data is used to fine-tune DeepSeek V3 base to improve readability and coherence. Stage 2 is reinforcement learning for reasoning. Here, same reinforcement learning pipeline as R10 is used, focusing on reasoning-intensive tasks such as coding and math using the same rule-based reward models. This time, an additional reward for language consistency is used to help the model stick to the same language. Stage 3 is rejection sampling and supervised fine-tuning. At this stage, a large synthetic dataset is generated using reject sampling, focusing on writing, role-playing, and other general-purpose tasks. The model from Stage 2 is used with DeepSeek V3 as a judge to generate 600,000 reasoning-related samples and 200,000 samples for writing, role-playing, and other general-purpose tasks using portions of the supervised fine-tuning dataset of DeepSeek V3 or regenerating them with chain of thought included. Stage 4 is the final stage, and it is called reinforcement learning for helpfulness. In this final stage, group relative policy optimization is used again with a combination of rule-based and outcome reward models to improve the model's helpfulness and harmlessness. This leads to the final DeepSeek R1 model. An important note to keep in mind here is that Monte Carlo tree search or process reward models were not used in DeepSeek training. Rule-based rewards focused on accuracy and format proved more effective than complex rewards models. Another point to note on the training data used for this model is that in China, copyright laws and intellectual property enforcement are often less stringent, which could allow for the use of data or methods that might not be permissible elsewhere. Also keep in mind that China has approximately 600 million static and mobile surveillance cameras installed throughout the country. This includes cameras on automobiles and trains. These cameras are continuously collecting new data. This enormous databank may be accessible to Chinese AI labs, including DeepSeek, for their model training. In conclusion, the rapid progress of AI development in China represents a significant shift in the global technological landscape, challenging the long-held belief that only large, well-funded American tech giants with vast computational resources and elite talent can lead in AI innovation. While DeepSeek's achievements are impressive, it's important to consider the economic context. Lower labor, living, and operational costs in China contribute to their ability to develop advanced models more affordably compared to the US. Nevertheless, this cost advantage only partially explains the scale of their progress, which is also driven by innovative approaches to AI development that prioritize efficiency over brute computational force. China's new large language model has disrupted the scale and brute computational force narrative, proving that groundbreaking advancements are possible without the billion-dollar infrastructures typically associated with AI development. DeepSeek's R1 development suggests that success in AI may no longer depend solely on massive GPU clusters, vast data centers, or concentrated elite talent pools, raising the possibility that smaller teams with smarter approaches could achieve comparable results. For US-based companies like NVIDIA, this shift poses a serious threat. Their business model relies heavily on the sale of high-margin specialized GPUs. If AI models can be efficiently trained on less expensive hardware, such as consumer-grade gaming GPUs or alternative platforms like those from Cerebras, the demand for costly high-end GPUs could decline sharply. This scenario mirrors recent historical disruptions, such as the transformation of the telecommunications industry in the late 1990s with the introduction of dense wavelength division multiplexing, abbreviated as DWDM. DWDM technology exponentially increased fiber optic capacity without requiring new physical infrastructure, thereby drastically reducing costs and reshaping the global telecom industry. The implications of this AI disruption are profound. AI development could become more accessible to a broader range of organizations and individuals, intensifying global competition and diminishing the strategic advantages, or moats, previously held by big tech companies. Hardware costs are likely to fall, and the barriers to entry for AI development will decrease significantly. While industry leaders like OpenAI, Google, Meta, and Anthropic will undoubtedly adapt and integrate these new efficiencies, the era of solving AI challenges by simply adding more computational power is coming to an end. This moment feels like an inflection point in technological history, comparable to the rise of personal computers or the shift to cloud computing. AI is poised to become both more affordable and widely accessible, fundamentally changing the competitive landscape. The real question is not whether this shift will disrupt current market leaders, but how quickly it will happen. The push toward open science and open source AI, exemplified by initiatives from organizations like Hugging Face, further accelerates this trend, ensuring that the benefits of these advancements are shared globally. This evolution in AI signals a future where AI is not just the domain of tech giants, but a field open to diverse contributors worldwide. We hope you found this video interesting and informative. Thanks for watching, and please stay tuned to our channel for more content like this.